Welcome back to another video on diagonalization. Let's get it. We are going to continue with, again, diagonalization examples, but this time we are going to do linear transformations. Y'all remember those? So fun. So there are ways we can people can ask these types of questions that involves linear transformation. So I'm going to do a couple of these examples. It's going to be a short one and then a little bit longer one, quote unquote. So hopefully we could do this all in one video, so let's get started. So this example, it tells us to find a basis B for the domain T such that the matrix T is relative to B is diagonal. In other words, just find a diagonal matrix. It's it's pretty not necessarily straight. Well, it's pretty straightforward, but the way they word it, it's just kind of weird. They're weird. So for the first one, we have P goes to 1 and 1 for A. B of x is equal to a plus 2b quantities times x. And so this one is a polynomial one. So we'll do a little bit of review with polynomials on how to put them in a matrix. So we are going to put this in a matrix. Remember, when we're converting with polynomials, this will be your constant and this will be your x. And so we're going to do 1, 0. And then 1, 2, because this is going to be your A, this is going to be your B. So now we have to do is find the eigenvalues, so that involves the characteristic equation. So we have 1 minus lambda, 0, 1, 2 minus lambda, and so that's just simply equal to 1 minus lambda times 2 minus lambda minus 0, which is equal to 0. We have lambda is equal to 1 and 2, and so when lambda is equal to 1, we get 1 minus 1, 0, 0, 1, 1, and so our eigenvector will be 1, negative 1, and then when lambda is equal to 2, we'll have negative 1, 0, 1, 0, and so the second column will be a 0, so that could just be anything, and so our eigenvector, which is B, second column, so the second row will be anything, but because we can't get rid of the 1 or negative 1, that would be 0, this could just be 1. And now our bases, so remember back in the last couple examples, we called our invertible S. Well, now we're going to call this our bases, because that's what it's asking for. So our bases is equal to 1, negative 1, and 0, 1. And that is our answer. We want to put this in like some polynomial form. We'll have B is equal to 1 minus x plus, or not plus, comma 1. And that is our, no, not 1, it's not 1, it's x, because this is x. This is our constant. So this would be x. And that'll be our answer. Now for the second one. So it's going to go from t 3 to 3, and then take in x, y, z, and it's going to give us this output. Again, first thing that we have to do is put this in a matrix. And so this gives us 1, 2, 3. So we're going to have a 3 by 3. So the first one will be the first thing, which will be the x, y, and z. So it'll be negative 2, 2, negative 3. And then we'll have 2, 1, 0. No, that's not 0, it's negative 6. And then lastly, we'll have negative 1, negative 2, 0. So again, we have to find a characteristic equation. So we have negative 2 minus lambda, 2, negative 1, 2, 1 minus lambda, negative 2, negative 3, negative 6, and negative lambda. Unfortunately, there isn't an easy way to do this, so we got to do this the long way. So this would be negative 2 minus lambda multiplied by 1 minus lambda times negative lambda minus 12. And then this would be minus 2 times I'm going to do the other one. So this would be negative 2 lambda minus 6, and then plus negative 3, so it'd be minus 3 times whatever is left over. So this would be 2 times negative 2, which would be negative 4, and that's a y. Let's fix that. Minus negative 1 times 1 minus lambda, so this would just be plus 1 minus lambda. And so now we're going to try to see if we can factor out a linear. So we're going to simplify this a little bit further. So it'll be negative 2 minus lambda, and this will be negative lambda plus lambda squared minus 12, and this would be plus 4 lambda plus 12 plus 12 minus 3 plus 3 lambda. And then this would just be negative 2 minus lambda. This becomes lambda minus 4 times lambda plus 3. And this would be plus 4 plus 3 is 7 lambda. And then 12 plus 12 is 24, minus 3 is 21. We can factor out the 7, so we have lambda plus 3, and that is equal to 0. Interesting enough, we have a lambda plus 3 that we can factor out. So we are left with lambda plus 3 times lambda minus 4 times negative 2 minus lambda plus 7. And so the lambda plus 3 stays. And then this becomes negative lambda squared plus 8 plus 7, which would be plus 15. And then this would be negative 4. No. This would be 4 minus 2, but plus 2 lambda. And then we can factor this out with a negative lambda. This would be positive and positive. So this would just be minus 3, then lambda minus 5. And that will be, all of this will be set equal to 0. And then we'll see that we'll have our lambdas or eigenvalues to be negative 3, which is this part right here. And then we'll have 5 and 3. So 3 and 5. Wait. No, negative. This would be negative because it would be negative 3. Yeah. Negative 3, 5. Or we'll have 5 and negative 3 with a multiplicity of 2. So now we have to find our eigenvectors, and we'll pretty much be done. So we can do the easiest one, which is when lambda is equal to 5. And so that will give us a negative 7, 2, negative 1, 2, negative 4, negative 2, negative 3, negative 6, negative 5. And so to find the vector, again, we'll do a little bit of guess and checking. Second row looks like it's the easiest one. So we can simply do negative 1, 1, and then negative 1. So that'll be negative 2 minus 4 is negative 6. Plus 6 is 0. Okay, so that one looks like it checks out. So the third row will be 1 minus 2 minus, that's not going to work. Okay, so this one is not going to work. Let's try this again. how about let's get rid of the first one. So we have -7. Let's keep that one. Actually make this positive. And so now we'll have -3. So we have -3. Keep that one. And that would be 4. So this would be -2. And so that, okay, so the first one checks out. The second one will be -2 plus 8 minus 6. That would be 0. The last one we have 1 plus 4 minus 5 is 0. Okay, this one checks out. Cool. All right, so now for our last one is when it's -3. So now this one, even though it has a multiplicity of 3, we still need to see, we can't be 100% sure that this is not diagonalizable, because we still haven't checked if the geometric multiplicity is equal to the algebraic. We know that the algebraic is equal to 2, so now we need to check to see if the geometric is also equal to 2. So when we plug that in, we will have 1, 2, -1, 2, 4, -2, -3, -6, and 3. And so we can see that our rank will be, so this one and this one are the same. At the same time, it is also a multiple of this one. So this will have a rank of 1. So our null is equal to 2, which is equal to our geometric, which is equal to our algebraic. So yes, this is still diagonalizable. So we can find our vectors, and our eigenvectors will be 2 of them, because our nullity is 2. So that means there'll be 2 eigenvectors for this one. And so the first one is, I think we could just do 1 for all of them, because it'll be 1 plus 2 is 3 minus 3. Yeah. So 1, 1, 1 is the first one. And then second one, because they're all a multiple of each other, we can just only figure out how to zero out one of them, and now zero out the rest of them. So we have 1, 1, 3. What is another one? 1, oh, 4. So 4. So it'll be 1, and then this would be -2, then -1. I think. No. It's -2, 1. It will be, hold on. So 1, then, so it will be -4 plus 1, -3 plus 3 is equal to, so this would be -1. And that will pretty much be it for this one. And so now to find our bases, it will simply just be the eigenvectors. So it'll be -1, -2, 1, and then 1, 1, 1, 1, -2, -1. And that will be our answer. Again, if you want to put this in kind of like vector notation, how we write every basis, it would just be the rows. So it'll be 1, 1, 1, then -2, 1, -2, and then lastly 1, 1, -1. Yeah, that's pretty much it for this example. This is the only example I will have with linear transformations, and I will see you in the next one.